Okay, so here's an example of the rational um, equation word problems we've been doing. And these are called combined rate problems. So it's two different rates that equal to one total time. Um, so the idea is that the total time is going to be equal to the time, sort of time one plus time two. So I'll show you what I mean by that with this example. So a kayaker spends an afternoon paddling on a river. She travels 3 miles upstream and 3 miles downstream in a total of 4 hours. In still water, the kayaker can travel at an average speed of 2 miles per hour. And then the question is, what is the average speed of the river's current? So, um, so like I said a second ago, the idea is that total time is going to be equal to, in this case, the time upstream plus the time downstream. Now notice we only know one of these things. The only thing we know is the total time. We don't know how long it took her to go upstream. We don't know how long it took her to go downstream. We just know that both together took 4 hours. So we need to figure out an expression for these two things, time upstream and time downstream. So total time is 4 hours. So 4 is equal to what? So these are rates, the time upstream and the time downstream. Remember, a rate of speed, just kind of come down here in this brighter blue color. A rate, which will end up being the time there, is going to be equal to distance over speed, how fast they were going, or average speed. So we need to figure out that for each of these, time upstream and time downstream. So we know in both cases she went 3 miles. So 3 miles upstream and 3 miles downstream. So 3 over her average speed plus 3 over her average speed. So the speed of the current is affecting her speed. So she's probably, well, not probably, but she's almost definitely going faster downstream, right? Because the current's helping her. So her speed is going to be faster. So this says she went upstream first. So the current was kind of going against her at first. She's trying to move upstream and the current is going against her. So it's slowing her down. So in still water, she would have been going, in still water, sorry, she would have been going 2 miles an hour. And the current, while she's going upstream, is going against her. So she's going slower than 2 miles an hour. So under this first part, we're going to put 2 minus c. That is 2 miles per hour minus the current, the speed of the current. So then you can probably guess what we're going to do under the next one, because now she's going downstream. So now she has the current pushing her along, helping her out. So she's going now 2 miles per hour plus whatever push the current's providing. So hopefully this setup, and that's the hardest part, is setting this up. So hopefully this setup makes sense. So maybe an easier way to think of this is just that you've learned in physics that speed or velocity is distance over time, right? So maybe a better way to think of this is time instead of a rate. because it's timed upstream and timed downstream. So speed is distance over time. So then if we want to solve for time, we could multiply both sides by time, and we'd have that, and then divide by speed. And that means that time is equal to distance over speed, which is what this is, distance over speed. That's the time. Maybe time is a better way to think of it instead of this rate that I said. So that's how we get these times. The reason we don't have to do that over here with the total time is because we know the total time. The total time was 4 hours. So each of these are expressions of time, where one, the current is hurting her. She's going upstream, so she's going against the current because, well, hopefully you know in a river a current flows downstream. So so when you're going upstream, it's harder. You're paddling against the current. It wants you to go backwards, and you're trying to paddle up. And then when you're going with the current, it pushes you. It helps you. You don't have to pedal. I mean, you don't have to pedal as hard. Of course, here we're assuming she's pedaling just as hard both ways. Okay, so now we just have a rational equation that we need to solve, which we know how to do. Let me get rid of those two little circles I just made. Okay, we know how to solve a rational equation now that we've set it up. So we need to remember to get rid of all the denominators. So we're going to multiply everything by all the denominators. So let's do that. Let's bring our problem down here, and I'll color code it so that you understand what I'm doing. So I'm going to take 4, and I'm going to multiply it by 2 minus c and 2 plus c, because those are both denominators. I'm going to end up running out of room if I don't write smaller. I can give myself a little more room, I suppose. Okay, and that's equal to 3 over 2 minus c, and I'm also going to multiply that by 2 minus c, 2 plus c. And then I'm adding 3 over 2 plus c and multiplying 2 minus c, 2 plus c. Okay, so now we've got this big equation that we need to simplify. So first let's figure out what cancels out. Well, on this left-hand side, nothing cancels because there's no denominator. But over here, things cancel. 2 minus c's cancel. And over here, our 2 plus c's cancel. So now we just kind of have to multiply everything out, and that might get a little hairy. So I'm going to give myself some room, but it's nothing difficult. So let's start with this part right here. We'll have 2 minus c, our little box, times 2 plus c. 2 times 2 is 4. This is negative 2c. This is positive 2c. And this is negative c squared. My c's are looking kind of funny. I don't usually write my c's like that. I'm not sure what's happening. Okay, but anyway, this comes out to be our c's, 2c's cancel. Negative 2c and a positive 2c cancel out. So we're left with 4 minus c squared. That's fine for now. 4 minus c squared is equal to, okay? So now we need to multiply, we need to distribute, just because these both are gone, because they canceled out. So we're just multiplying this 3 and distributing it here. So 3 times 2 is 6, and 3 times c is 3c. Excuse me. And then over here, same thing. Remember, both of these things we crossed out are gone. So we're just distributing this 3. So 3 times 2 is 6. And 3 times negative c is negative 3c. Okay, so now we've got something we can work with. We know how to solve this. We want to get it into standard form, and then it's a quadratic that we can solve. So first, hopefully you recognize that positive 3c and negative 3c will cancel out. So those will go away. 6's will not go away because they're both positive. So we've got 4 minus c squared is equal to 12. 6 plus 6. All right. Now we can, excuse me, subtract 4 from both sides. Oh, I'm sorry. I made a mistake. Over here, I've still got this 4 on the outside that I forgot to distribute. So I multiplied down here, in this part, I multiplied the 2 minus c times 2 plus c, but I didn't involve the 4 out here that was out front. So I also need to distribute this 4. Sorry about that. Okay, so 4 times 4 is 16, and 4 times negative c squared is minus 4c squared. Okay, there we go. Now we're on the right path. Okay, so now we want to subtract 16 from both sides, trying to get the c by itself. In this case, we can, because there's no other c. There's just one c, so we can get it by itself. So here the 16's cancel, and we're left with negative 4c squared is equal to 12 minus 16 is negative 4. Okay, so now we can bring this up here, and we can divide both sides by negative 4, and that will get rid of the negative 4's over here. It actually turns these into a 1 too. So then we've got c squared is equal to 1. So now we can just take the square root of both sides, trying to get rid of the squared. Sorry, square root of both sides. And over here, the square root cancels with the square, and we're left with c is equal to positive or negative 1. So that's our answer. But in the case of the problem, what makes sense? Does it make sense to say that the current has a speed of negative 1? It really doesn't. Speed can only be positive. So our answer in all reality is c is equal to 1. This current is going at 1 mile per, oh, sorry. And really it's just 1 mile. It's not even multiple miles. So it's going at 1 mile per hour. So that's our answer. So the hardest part of this is just setting it up. But hopefully this makes sense in terms of recognizing that total time is equal to time 1 plus time 2, whatever the problem may be. It doesn't have to be a kayaker. It could be a jet going with the air current and against the air current. It could be 2 people working together. When one works by themselves and then the other works with them. It could be anything, but this is the same setup. So hopefully that's helpful to you in solving for these problems.